Hello everyone, and welcome back to my supplemental videos on linear algebra. In this video I want to talk a little bit about linear independence, and in particular I want to talk about the Wronskian. So we've discussed in class linear independence a little bit, and one major question is how do we determine whether or not a set of n functions in the function space Cn-1, so these are the functions with n-1 continuous derivatives on the domain AB. We want to know when are these functions going to be linearly independent. And so you'll remember that the defining relation for linear independence is that a linear combination, C1F1, C2F2, etc., up to Cn times Fn, if this linear combination equals 0, so if we add these functions up and get 0, then for these functions to be linearly independent, the only way to do this is if the unknown constants, the C1, C2 up to Cn, if those are all 0. And so in this scenario, each of these vectors, the vectors are the functions f1 through fn, each of these functions have at least n-1 derivatives. And so what we can do is we can take the derivatives of the implicit derivative of the entire equation here, and when we do that, we remember that the derivative itself is a linear operation, and so it can be broken up over the addition signs and the equal sign, of course, and the constants can come out of the derivative, and what we end up with is a system of n equations with n unknowns. So our next equation will be C1 F1 prime plus C2 F2 prime, etc. And so this is the equation that we get for the first derivatives. And we would continue on until we have all n-1 derivatives, but that's going to be n total equations. So this would be n-1 in parentheses. That's the notation for the n-first derivative, etc. And so all of these, for these functions, if these are linearly independent, then all of these equations must be true at the same time. Okay, and the coefficient should be 0 for all of them. And so what we can do is now rewrite this formally. We say formally because the vectors here are functions, right? So we can rewrite this formally as a matrix product, though. And so we can write this as the matrix W, which would be kind of, in this case, the unknowns are the C's, C1 through Cn, and the coefficients are these functions now. And so the matrix W would consist of F1, F1 prime, all the way down to F1 n-first derivative in the first column, and we fill out the entire matrix with these functions and their derivatives. Okay. Oops. So that's just the function Fn, and then we go all the way down to the Fn n-first derivative. And so as a matrix equation now, this here, so W is just the matrix itself. All right, and then we would have to multiply by the vector of the unknown constants. And as a matrix equation, this entire product should equal to 0 vector on the right-hand side. And so we know from our studies that this system will have only the trivial solution if the determinant of this matrix is non-zero. So we compute something called the Wronskian, and so the Wronskian is going to be the name of the function that we get by taking the determinant of this matrix W. Okay, so the Wronskian is the determinant of W, but that's going to be a function of X in this scenario. Okay, so we get this theorem then that these functions will be linearly independent if the Wronskian is non-zero at any point in the domain. So this is key. So if there exists a point, you could read this as if there exists any point in the domain of the common domain of the functions where the Wronskian is not equal to 0. So if it's non-zero. Now, the key thing that we want to notice here is that this is a one-way theorem. Okay? If we can find a point where the Wronskian is non-zero, then we get our answer. We get the linear independence that we're looking for. However, if we can't, and if the Wronskian is always equal to 0, then we learn nothing and we have to do more work. So we have to take a different approach at that point. Okay, and so we'll come back to this idea of the one-way theorem in a few minutes. So let's do a couple of examples. The first one is we want to check and see if these two functions, e to the x and e to the minus x, are linearly independent in CR. So this is the space of continuous functions. these two functions actually have infinitely many derivatives. So they really live in a space called C infinity. There's infinitely many derivatives. All right, but we check this the same way. So we want to build the matrix W first. And so the matrix W, we start by just putting these functions in the first row, e to the x, e to the minus x. There's two functions, and so that gives us two columns in our matrix. And now to build the rest of the matrix, we take the derivatives of these. So the derivative of e to the x is itself. Derivative of e to the minus x is minus e to the minus x. Okay, and now we take the determinant of this. So the Wronskian is not this matrix, it's the determinant of this matrix. So we compute our Wronskian, and we see that when we multiply these together, we get minus e to the x times e to the minus x. And then we have to subtract the off diagonal. So minus e to the x times e to the minus x. Okay, and now when we multiply these e to the x times e to the minus x, we add the powers, we get 0, right? So this is just going to be minus 1, which is negative 2. And of course, negative 2 is not 0, ever, right? But it's especially so we could just, it's never going to be equal to 0 on our entire domain. And so by our theorem on the previous slide here, by this theorem, that means that these two functions, e to the x and e to the minus x, are linearly independent. So the answer here is yes, linearly independent. And the question even says that they are linearly independent, but now we've shown it. Okay, let's go to a slightly different example now. Now we want to show that these two functions, x squared and x times the absolute value of x, are linearly independent in the same space. Now these two functions don't have infinitely many derivatives. Well, this one does, x squared, but x times absolute value x does not have infinitely many continuous derivatives, I should say. But regardless, let's start by trying to do the Wronskian. So we make the matrix. We write down the functions first. And then we take the derivative. So the derivative of x squared is 2x. And the derivative of x times the absolute value of x turns out to be 2 absolute values of x. And so you can work this out by writing this as the absolute value as a piecewise function, and then taking the derivatives of the pieces and making sure that the continuity works out. All right, and then we take the determinant of this matrix. So when we take the determinant, we get, again, the determinant of this matrix is always going to give us a function. And so this will be the function w of x, which is equal to 2x squared, absolute value of x, minus 2x times x, so another 2x squared, absolute value of x. And of course, these are the same, and so this equals 0. All right, and now this is equal to 0 at all values of x. So therefore, our theorem does not apply. So the theorem that we had a couple slides back, we can't find this, right? So this x naught, where x is not equal to 0, the Wronskian is not equal to 0, this point doesn't exist. And so that doesn't mean that the functions are linearly dependent, it just means that we have to do more work, okay? It means that this Wronskian method was not good enough. And the more work we can do, so these two functions, if we want to show that they're linearly independent, then we need to check this property, that c1 x squared plus c2 times x absolute value of x equals 0. But the only way to get these are for c1 and c2 to both be 0. Okay, and to do this, to make this equation a little more manageable, we can pick some values of x, some convenient values of x, we might say. So if we choose x equal to 1, then this equation becomes c1 plus c2 equals 0. This has to hold for all x and all real numbers, right? According to the